Okay. So our next speaker will be Ruoyu from Chinese University, Hong Kong, Shenzhen. This is a teaser session. Basically, Ruoyu is going to present a predictive control framework for Manipulator on a disturbed seaborne platform. Ruoyu, could you hear me?
Yeah, I can hear you. I can hear you. Thank you, okay. Dr. Wang.
I can see your screen.
Yeah. Okay. So shall we start?
Yes, please.
Okay.
Please go ahead.
Hello, everybody. Today I'm going to present a predictive control framework for Manipulator on a disturbed seaborne platform. As we can see in these two videos, it's a challenge for UAV to land on a disturbed platform. And it is more difficult to land a UAV on a small surface vehicle because a surface vehicle is more unstable. So we are going to use Manipulator to help the UAV land safely and accurately. This is an experiment to catch the UAV on a disturbed platform. And the Manipulator is mounted on a rotary platform whose motion is 0.16 Hertz and the amplitude is 10 degrees. The position of the UAV is measured by the motion capture system, and the Manipulator is controlled by a Jacobian transpose method. And the end effector of the Manipulator is designed to tracking the objective by a proportional controller. We can see that the response of the Manipulator is very slow. And after about 3 tries, at last it will catch the UAV successfully. But if we increase the frequency of the base motion to about 0.48 Hertz, we can see that it will be very hard to control the motion of the Manipulator. Recently, more and more research shows that MPC has a good tracking performance. So to stabilize the end effector motion, we proposed an MPC controller. The control framework consists of 3 parts. In the gray box here, it's a high-level controller. The trajectory is generated here by the predicted USB motion. And the yellow box is the MPC controller. The model in MPC takes the delay of each joint controller into account, and the parameters in the MPC is updated in real time by an uncertainty observer. The MPC will feed the velocity command to the low-level joint velocity controller in the blue box. And what in the right side is the simulated USB motion based on the collected data from level 1C condition. In this framework, firstly, the roll and the pitch of the USB are predicted in real time. And the black line is collected data from a real USB, and the blue lines are the predicted motion. We can see that the predicted motion is agree with the real motion, which will be further used to generate the reference trajectory for the MPC controller. The dynamic of each joint is estimated by a first-order delay model. That's exactly what we mentioned in just before. And this is the model. The TM is the time constant, which will be observed by an uncertainty observer, and it will also be updated in real time. The model predictive controller is formulated based on this model. To verify the feasibility of our method, we did a simulation. And this is the result of the simulation. On the left side is a platform before stabilized, and on the right side is a platform stabilized by our method. We can see that our method works. We also compared our method with an inverse kinematics controller. And in this simulation, we let the manipulator checking a circle in a inertia frame, and at the same time, the base is fluctuating. The motion of the base is generated by the USV motion collected from at sea. And according to this simulation, we can find that our method has a better tracking performance compared with traditional method. Our future work is to implement this method to a real manipulator. Thanks for your attention.